Okay guys, so I tried to make a video to sum up everything, and I've got torque, angular momentum, energy, pendulum, springs, restoring force, the X equals formula, and then the relationship between rotational and kinetic energy. I've got the 6 questions from that multiple choice sheet on that paper I gave you today. And I figured we'll just go through this. So it's going to take a second, but just bear with me, and if you want to skip, you're welcome to skip. So with torque, the first thing to understand is that the torque is equal to the force times the radius. Also, torque is equal to I alpha. What this means is that if you have a torque acting on an object, it has to be provided by a force acting at a radius. But if you have a torque, then it is going to cause the moment of inertia to have an angular acceleration. All right. If torques are in equilibrium, then the counterclockwise torque has got to, the clockwise torque has got to be equal to the counterclockwise torque if they're in equilibrium. And so what this means is that the F1 times R1 has got to equal F2 times R2. Or if there are more than one forces on one side, you could have F3, R3, right? So you could have more than one force acting on one side of the rotation versus the other side of the rotation. Whatever the case, if it's in equilibrium, they have to be equal to one another. Okay, each side, the counterclockwise rotation and the clockwise rotation have to be equal. Keep in mind also where you're measuring the rotation from. So we're right here looking at the ABC thing. A, B, and C representing the different points of rotation. For instance, wherever you are, like for instance, this is a board, right? So this is a board. Wherever you are on the board, the weight, the thing providing the force, will be in the middle. And then the radius will depend on where the center of rotation is. So if the center of rotation is at A, then it would be the gray thing for the radius. If it's at B, then it would be R for the red for the radius and blue for the radius if it's at C, right? So on all of these, you're measuring to where the mass is acting at. If you just have a force, you just, like if it's just a force, you just say that's where the force is acting. But if it's the weight, it's acting from usually the middle of the board. That's usually what you'll be dealing with. This last thing over here is if it's not in equilibrium, then, for instance, we did a couple problems where we had masses hanging from 2 different size radii that were connected. And keep in mind that if like in M2, this one, this particular one that we're looking at, M1 and M2 are the same. If M1 and M2 are the same, notice that it would go this way because M1's, even though the force is the same, so both of these two would be the same. Since R1 has the bigger radius, this is going to make this torque, Since R1 has the bigger radius, it's going to make this torque greater than this torque. So it will turn in the direction of M1. So that's torque. Angular momentum. Most important thing about angular momentum is that angular momentum does not change. So let's just write L. L doesn't change without a torque. Also remember that P, the linear momentum, doesn't change without a force. Okay? And then always remember that L and P, angular and linear momentums, don't mix. Okay? For this one also, remember that I is equal to mr squared. If the mass is farther out, it leads to a bigger I. Think of the skater arms. Like the skater has her arms out, it's a bigger I, so she has a slower omega, and when she brings her arms in, she has a faster omega. So look at the relationship here, look at the formula. Most of the time this angular momentum is going to be staying constant. So if you increase the I, then the omega has to go down. If the omega somehow increases, then somehow the moment of inertia probably decreased if the angular momentum is staying the same and there's no we're assuming in both of these cases there's no outside torques. So like, for instance, this one right here would be if the skater put her hands out, she would be increasing her moment of inertia and her spin would slow. And then this one would be if she brings her arms in, decreasing her moment of inertia and her angular speed would increase. Energy. First period. Be sure you look at this. I lied to you. I apologize. I did not mean to. I thought something was wrong, but I just kept going. And what I said was that the potential energy was connected to the x and the kinetic energy was connected to the velocity. Well, that's not 100% wrong. It's just not 100% right either. I got it 50% right. They are connected. The problem is that since these are squared, they're not negative. They can't go negative. So rather than going up and down like x does, when x goes below the line, the potential energy will come back above the line. So, for example, if I can just quickly jot this down maybe. If this was the x graph would look like this. It would be going, oops, sorry. Let's try this again. The x graph would look like this instead of, yeah. So the x graph would be going up and down, but whenever the x graph is up, the potential energy graph would be up, but whenever it's at its peak on the bottom, the potential energy should be at its peak at top. So they do go together, but they're just not perfectly aligned. So the energies, the total energy of the system should stay constant, so that was right. And the potential energy and the kinetic energy should be opposites of each other. Notice these are opposites. And if the x is up, it means the potential energy is at its greatest point. And if the potential energy is at its greatest point, then notice that the kinetic energy is at its lowest point. So kinetic energy and potential energy should be opposite of each other. The kinetic energy should be opposite the potential energy, but it doesn't ever drop below the zero line. It stays above zero because you can't have a negative amount of energy. Now, interestingly enough, sometimes when we deal with spring potential energy, when you're dealing with gravitational potential energy, occasionally they will assign that as negative. So just be aware. Sometimes that comes up as negative. But when we're dealing with the spring energy and the pendulum energy, it's always going to be positive, and it's always going to be positive. So just keep this in mind. This is a special case. If you're talking about gravitational potential energy, occasionally they will call that negative. Just be aware of that. But for the sake of pendulums and springs, they're going to call those both positive. Okay, pendulums. What's important about a pendulum? Well, this is the formula that you were given. All right. Occasionally you'll see it written like this as well, which, as you can see, they essentially just took out the square root. And so what they did to take out the square root was they squared everything else. So they get rid of the square root by squaring the time, the 2, the pi, and then the L over G don't get squared because they're underneath the square root. Know that G on Earth is 9.8 meters per second, so that's what would go in here if it's on the Earth. But if it's not on Earth, you would have to somehow use this formula to figure out what G was. All right? That might be important. You need to know that mass doesn't matter with a pendulum. The mass isn't important. The distance pulled back doesn't matter either. So it doesn't matter how far you pull it back, and mass isn't important. Okay, springs. The same thing is true with the spring. You can square it. So this is the formula you're given, but you could square it to get rid of the square root. With a spring, gravity does not matter. T is the same even if it's hanging on even if it's hanging or horizontal. So it doesn't matter whether the spring is like this or some combination or somewhere in between. The period will be the same. The difference between these two, vertical versus horizontal, is that X will be stretched more if hanging. And then also with springs, just like with pendulums, the distance pulled back is not important. All right. Just as a little note, for either spring or pendulums, please remember the period is equal to 1 over the frequency. So if you have the frequency, you can find the period, and if you have the period, you can find the frequency. Restoring force. So the restoring force was this thing we talked about today. It's something that I talked about, but didn't we mentioned it. I just didn't go into near enough detail. It was kind of like a one-off thing that I said, and so there's a good chance y'all didn't hear it, which is my fault, not yours. So the restoring force is in pendulums and springs. The bigger the restoring force, the more acceleration and the shorter the period. The restoring force is what's getting it back to equilibrium. So the bigger the restoring force, the shorter the period is. With springs, you have to make sure M is the same. If you do not make sure if M is not the same, then you're going to do F equals MA to figure out which one is got a bigger restoring force. This formula, again, not super important to know what how to use it as much as know what the things inside mean. So X is the position, A is the amplitude, 2 pi is just 2 pi, F is the frequency, and T is the time. Okay? So this kind of sums it up. This is 11 minutes, so hopefully that gives you some basic... Oh, I forgot about this one. I'm sorry. Rotational versus kinetic energy. So important to note that kinetic of rotation is 1/2 I omega squared. Kinetic energy, remember, is 1/2 mv squared. So what this means for you, there's several different things it can mean. These are the two most common problems. If you have a bigger I, it means you have to work more to rotate, so it will have a slower linear speed. So if two objects start off with the same potential energy, and one has a bigger I, then that means that this term here is going to have to be using a larger amount of the potential energy. If the I is smaller, it doesn't have to use as much potential energy, so more of it can go into the 1/2 mv squared. So if you have a big I, essentially what you're doing is you're increasing the amount that has to go into rotational. That's going to increase, and you're decreasing the amount that can go into the kinetic energy. Okay. Also, sliding objects get to the bottom first because they do not have to lose energy lose energy to rolling. So if you're sliding, your potential energy is just equal to your kinetic energy. But if you're rolling, your potential energy is equal to the rotation plus the kinetic, the regular linear kinetic. So you got to take that into account. Also keep in mind there's a difference between sliding and slipping. Slipping means friction's involved, and it means you would need to add a friction times distance thing here. So sliding just means it's going down the hill without friction. Slipping means that your wheel isn't rotating smoothly. It's like you're peeling out. Okay, so let's work some problems and see what we can do. So here's M1. This is on the problems that we were looking at earlier. M1 says, this is on the problem set that I gave you today that we just did the warm-up on. This is some multiple choice. This will help you out if you stick with me. So an object attached to a spring oscillates horizontally without losing mechanical energy. The displacement versus time graph for the object is shown. Which of the following correctly represents the kinetic energy versus time graph for the same object over the same interval? Okay, so first of all, we need to know that X and kinetic energy are on opposite tracks. So I already wrote that in gray, didn't I? My bad. X and K will be opposite, but K has the V squared in it, so it will always be positive. So basically what you can look at to rule stuff out, K has to always be positive, so we can rule out A and B, so we're between C and D. And essentially you know that the K has to be the opposite of the X, so if X is up at the beginning, K has to be down at the beginning, so the answer is D. Number 10, an ideal rubber ball is bouncing vertically on a hard floor. It does not lose mechanical energy. This motion is not simple harmonic. All of the following are reasons for this, except so not harmonic. So basically, we're looking for a way that would make it harmonic. So the period of the motion depends on the amplitude. Well, if you bounce a ball, like if we bounce the ball from here to here and like have it going back and forth, and then do it from here to here and have it going back and forth, the period would change. This would be like t, and this might be 2t. So the period is dependent upon the amplitude for a bouncing ball, so it can't be simple harmonic. The force on the ball is not proportional to the displacement. Yeah, because like when you're dropping a ball, it doesn't matter where you look at it, it's always the force of gravity. So unlike the spring force or the pendulum, so with the spring force, remember, you have it stretched, and that x value, force, is equal to kx, and as it's moving in, the x is decreasing, so the force is decreasing, so the force is variable. With a pendulum, it's because the force of gravity is a component of the movement, is causing the movement, so it's a component of the force of gravity that's causing the movement, and as you change that angle as it's moving in, it changes what that force of gravity is. So that's not it. The gravitational force is trying to restore equilibrium. Well, that's true, because that's what's restoring equilibrium to the ball every time, is the force of gravity. And the equilibrium position is not at the midpoint of the oscillation. Equilibrium points for the ball would be at the top and the bottom, and the equilibrium points, so where it's moving and where it's not moving, equilibrium points should be in the middle for simple harmonic motion. So if it's a pendulum, it's going from here to here, and equilibrium's right here. If it's a spring, it's going from here to here, and equilibrium is right here. So the should be in the middle. So the answer should be C. All right, when a mass hangs vertically, it stretches a distance x and has a period t when set into oscillation when on the incline. How do the new equilibrium, stretch, and oscillation positions compare x to t? Let's see, let's make sure we know what's going on here. So when a mass hangs vertically, it stretches a distance x and has a period of t. So this is our original here, and this is our comparison. So we're using this one to compare it. But didn't finish that. Did I spell that right? We're going to go with I spelled that right. Okay, so first thing you need to know is that the period of the period should be the same regardless. So it can't be less than. So you know A and C are out. So now we need to know what's going on with the equilibrium stretch. So let's see. So the key here is that since this is on an incline, this one is just going to be pulling force of gravity down. This one's going to have spring force up. So whenever it's at rest, spring force should equal force of gravity, which means kx should be equal to mg, right? But here, the force of gravity is coming straight down, and it would really just be the force of gravity in that little component of force of gravity that would be acting on it. So it's a smaller component. So it'd be kx equals, well, if we call this theta, sorry, let me draw that a little bigger. Let's make this a little cleaner. So if this is force of gravity, and then we bring this out here, and we call this theta, okay, then this is the force of gravity in the x, and it would be equal to kx, in this case, would be equal to mg sine theta, right? So you have a component of it. So since this is bigger than this, the x is smaller, right? Because the force pulling it down is less. So you should have equal to, and the x should be stretched less, because there's less force pulling it down to begin with. M4. An oscillator consists of a 3 kilogram mass of 3 kilograms and a spring constant of 100 Newton meters. The position versus time graph for the oscillator 1 is shown. Oscillator 2 consists of the same 3 kilogram mass and a spring with a force of 400 newtons. If both oscillators have the same total energy, which is the graph position versus time for oscillator 2. So this is oscillator 1, and what we're trying to basically identify, we're going to just call the period of this one 1, and then we want to know what the period of the other one would be so that we can compare them. So what we do is we start with the period equals 2 pi m over k, and then we need to determine how is mass related and the spring energy related. Well, we know in the original it's 100 for the spring constant, and we know it's 400 in the second one. So that means our spring constant went up by a factor of 4, but we kept the same mass. So we're just going to leave mass as a 1 because the mass isn't changing. So when we go to do our ratio, we're going to plug in 1 for the 2 pi, 1 for the mass because it didn't change, and a 4 for the k because it increased by a factor of 4. And then the period of the spring would be 1/2. So in other words, it's moving 2 times as fast. So it should have 2 times the number of peaks and troughs. Okay, so correct response is C because we halved the period. So if the full period, let's just say this is 1 second to make it easy. If the full period took 1 second the first time, if we half the period, now it's going to be at half a second the second time. Okay. M5. On another planet, a simple pendulum is constructed that has a string variable L. For various lengths, the period of the pendulum is measured. The graph shows the square of the period plotted versus the pendulum's length. What is the approximate acceleration due to gravity on this planet? Well, I have t squared here. So instead of using this formula that we typically use, it'd probably be easiest to use this formula because everything's been squared already. So I can just pick a number and plug it in. So that's what I'm going to do, and I'm just going to pick 50 and 5. So just to back out here, whoops, I'm going to pick 50 and 5. So I'm going to plug in 50 for t squared equals 4 pi squared times 5 divided by g. And I'm going to solve for g, so multiply both sides by g and then divide by 50. So g is equal to 4 pi squared times 5 divided by 50. Okay, so I used my phone calculator, so I hope this worked out. But if you do this, I think it's 3.95 meters per second squared, which is d. We'll round it to 4. And that is indeed the correct answer, okay? So, just to take this a bit farther, you could technically, if you could figure out other things about this by using g equals big G m over r squared. So, for instance, if I told you that it had the same radius as the Earth, you could kind of figure out what the mass of the planet was. If I told you it had half the radius of the Earth, you could figure out what the mass of the planet was. If I told you it had 3 times the mass of the Earth, you could figure out what the radius was. So you could go to this problem and figure out stuff using that number if you wanted to, if you were so inclined. Seems like something you could do. All right, M6. A student measures the motion of a spring mass oscillator and calculates a regression equation based on the oscillator's motion. That equation is x equals 0.1 cosine 5.4t. The student takes down the amplitude and the angular frequency from the equation. Which of the following can the student calculate from these two values? Well, first of all, what can we learn from this? Well, you can learn that A is 0.1, and you can learn that 5.4 is 2 pi f. So really, you could say f is equal to 5.4 divided by 2 pi. So you've got a frequency and you've got an amplitude. So what could we do with that? Well, one thing we could easily do with that is figure out the period. Because remember, the period is equal to 1 over the frequency. So A is definitely an answer choice. So now we got to figure out what the other things are. So I've got the period now, so I've got this. Is there any way I could figure out the mass or the spring constant? Well, not really, because I have to have the mass and or the spring constant to figure that out. So I can't really figure that out because I don't have the spring constant. I can't really figure that out because I don't have the mass. So those two are out. So obviously the answer is D, but how? Well, one way to do it is if you do a deep dive into the physics textbook, you can do amplitude times omega. Another way is just to kind of think about it. If you know that it's going, let's just say it's going from 0.1 to negative 0.1 and then back to 0.1, so it's going back and forth, and you know the period, well, you could put it point at 0, and you would know if it's taking, once you find the period, you know it would be 1/4 of the period to go from 0.1 to 0. So you could do basically this: V average equals distance over time equals VF plus VI over 2. And you could do 0.1 for the distance it's traveling. This distance is traveling here. This would be your D. 0.1 divided by 1/4 of the period, the time it would take to get back to equilibrium, equals VF, which would be its max speed, because it would reach its max speed when it gets to the midpoint, plus the initial speed up here is 0 because it's not moving, divided by 2. And you could figure it out that way. Is this the most efficient way to do it? Absolutely not. You could do it that way, and you would figure out that it's D. The reason I didn't show you this, it comes up on the NIMSY packet. Whenever I was looking at the AP stuff, I never saw that formula mentioned. So I didn't go over this, but now you know. Vmax is equal to alpha, or amplitude. This is amplitude times omega. And remember that omega is basically just the frequency times 2 pi. To just give you a real quick rundown, the frequency, if you'll remember, is the rotation over the time interval, whereas omega is 2 pi over the time interval. So if you do, omega is essentially just 2 pi times the frequency, or you could say frequency is omega divided by 2 pi. So basically, the frequency is how long it takes to go one complete rotation. Omega is more an angular distance over time, so it doesn't necessarily have to go a full rotation, but if you divide it by 2 pi, you get the same thing. Okay? So that might be good to know. Just erase that. All right, so that's a 27-minute review, so hopefully some of you watch this. It should be very beneficial if you do. All right? If you watch this, write red on your paper. I'm just kidding. Don't write red on your paper. Let's see. What do we want to do? If you watch this, find the 5th word in M4, the 5th word in M4, and write that on your paper. Performing an experiment.